So think about every skyscraper, every bridge, every massive structure you've ever seen. They all rely on the ground beneath them, right? But what if I told you that the secret to solid ground has less to do with the actual dirt and rock and more to do with the empty spaces in between? Today, we're diving into two concepts that are absolutely crucial for engineers: porosity and void ratio.
Yeah, it sounds a little wild, doesn't it? That the key to building something enormous, something permanent, might actually be in measuring, well, nothing. We're going to see how those empty spaces, the voids between the soil particles, are really what tell us if the ground is strong enough to build on.
Okay, so first things first, we have to get our heads around what soil actually is. It's not just a solid block of dirt. It's way more interesting than that. It's actually a mix of a few different things. That's right. Any sample of soil you pick up is basically made of two main parts. You've got the solid particles, think tiny bits of rock, sand, clay, and then you have the empty spaces between them. We call those voids. And those voids can be filled with air or water or a bit of both. This super simple idea is the foundation for everything else we're about to talk about. So, if we want to know how much of our soil is just empty space, how do we measure that? Well, the most intuitive way, the one you've probably heard of, is something called porosity. Porosity, which we use the letter N to represent, is a really straightforward concept. It basically asks one simple question. If you look at the entire chunk of soil, solids and all, what percentage of that total space is just emptiness? And here's the formula for it, see? You just take the volume of all those voids, the air and the water, and you divide it by the total volume of the whole sample, solids plus voids. Then times 100 to turn it into a percentage. Pretty simple, right? But like anything, this measurement has its limits. It can't just be any random number. It's got to follow some basic logical rules. For starters, porosity has to be greater than 0. And why is that? Well, think about it. If a sample had 0 empty space, it wouldn't be soil anymore, would it? It'd just be a solid block of rock. So by definition, soil has to have some voids. And on the flip side, porosity has to be less than 100%. I mean, you can't have a sample that's all empty space, because then what is it a sample of? It has to contain some solids to even be considered a soil sample. So the volume of the voids can never be the total volume. And I love this. Our source material has a bit of fun with this. It poses the question, could you have a soil sample that's almost 100% voids? Basically just a cup of water with a grain of sand in it? And the answer is, technically, maybe you could make that argument, but in the real world of engineering, you'd just be a jerk. So for our purposes, porosity is always going to be somewhere between 0 and 100. Okay, so porosity seems pretty straightforward. It's intuitive, it's easy to calculate, but here's the plot twist. For an engineer who's trying to predict how the ground is going to behave under pressure, this simple little measurement has a huge hidden flaw. So let's imagine the immense weight of a new skyscraper pushing down on the ground. That soil is going to get compressed, right? The little particles are going to get squished closer together. So what does that do to our numbers? And this, right here, shows us the problem perfectly. When you compress soil, what happens? Well, the volume of the voids gets smaller, obviously. But because those voids are shrinking, the total volume of the whole sample gets smaller too. Now, think back to our formula for porosity. The number on top is changing, and the number on the bottom is changing. That makes it a moving target. It's just not a stable metric for an engineer who needs reliable numbers. So if porosity is kind of flawed for this kind of work, what do engineers use? Well, they needed something more stable, something they could count on. And that's where the void ratio comes into play. The void ratio, which we represent with an E, sounds almost the same at first, but it has one absolutely critical difference. Instead of comparing the voids to the total volume, it compares the voids to the volume of just the solid particles. And here's its formula. The magic is all in the denominator, the volume of solids. Let's go back to our compression example. When you push down on soil, you're squeezing out the air and water, sure. But are you changing the actual volume of the tiny bits of rock and sand themselves? No way. That part stays constant. It's our anchor. And this idea from our source material is the whole key. It says that any change you see in the soil's overall size is really just a change in how much empty space there is. The solids themselves don't change. So by using that constant value as our baseline, engineers get a measurement that's way more stable and predictable.
All right, so let's put these two side by side. Let's make this critical difference totally clear.
Here you have it, head to head. Porosity uses the total volume, which, as we saw, changes when you put it under pressure. But void ratio? It uses the volume of solids, which is constant. It doesn't change. Because only one variable in its equation is moving, the volume of the voids. The void ratio gives engineers a direct, stable, and super reliable way to predict what the soil's going to do. And that's why it's the engineer's choice.
So let's just boil it all down. Porosity is a simple idea. It makes sense at first, but because its denominator changes, it's just not stable enough for serious work. The void ratio, on the other hand, anchors its calculation to the constant volume of solids, and that gives engineers the rock-solid, reliable tool they need to build our world on safe ground. And that kind of leaves us with one last thought, doesn't it? We just saw how a tiny, subtle change in a simple ratio makes all the difference in the world of engineering. It really makes you wonder, what other simple, almost invisible forces are out there, quietly shaping the world all around us?